Hi everyone, so this will be a continuation from the first video in this series, which covered the first three sections of Chapter 9, and then this video will cover the last three sections of Chapter 9, so 9.4, 9.5, and 9.6. So, in the first couple of sections, we really focus more on why things dissolve, what type of things will dissolve in water, and what kind of conditions can affect the solubility of gases. So now what we're going to move into is talking about concentration of particles in solution, so that again we can move forward towards actually keeping track of reactions that happen in an aqueous solution. So concentration is going to be really important because when things are more concentrated, they tend to react more and faster. So that's what we'll pick up. So in general, when I say anything about concentration, right, I'm not talking, it's funny because this actually happened in one instance in grad school where we had an undergrad confuse concentration with like thinking hard. We are not talking about thinking hard. We are literally talking about how much stuff, in our case, the amount of solute that is in a given amount of solution. That's what we mean by concentration. And as a chemist or as a nurse, you're going to come into a lot of different ways to represent concentration. What we actually see on the bottom is the most common way to report concentration in chemistry, while you're seeing other less common, though still I've used all of them in my research and in daily life. So they're less common than molarity, but important to know because they are common enough. And that will be mass percent, abbreviated as MM. The abbreviation comes from literally the mass of solute over the mass of solution, so M per M. Volume percent, the same idea. It's volume of solute per the amount of volume of solution. So again, VV makes sense. And we can actually get a combination of the two. So if I knew the mass of my solute versus the amount of solution I had in volume, and then you'd have another way of representing concentration. The newest one will be molarity, and that's going to be, by definition, moles per liter. So this is kind of like a brief overview. We'll go through each one individually. So the first will be mass percent. And so we've already abbreviated. It's going to be M per M. And the equation for us is just grams of solute. And that should make sense because we're dealing with M on top. And then we have deals with grams of total solution. So it's a gram of solute that you dissolved plus the gram of solvent. This will give you a fraction. So to make it a percent, you multiply by 100%. And we're going to actually see, even though it changes for each of the next, I believe, the next three types of concentration we'll talk about, mass per mass, volume per volume, and mass per volume, the equation ultimately almost stays exactly the same. So it's just keeping track of what are you solving for. Another way you can represent this, because it's 100% of a mass, it is also equal to grams of solute per 100 grams of solution. It's another way of phrasing it. That basically comes out because you're multiplying it by 100. So to have an example, this is the only example we'll do for all three of them because it pretty much is going to be the same with minor variations. So let's just look at how one solution would be made if we know mass per mass. So it's saying when water is added to 8 grams of potassium chloride to form a 50 gram, oh, that's a really weird way of phrasing it, to make a 50 gram of KCl solution, the mass percent concentration is 0.16% M per M. So let's figure out why. And so I believe on the next slide I have this worked out. If not, we'll do it out manually. Oh, I do. Great. So I know that seemed weird when we were phrasing it, but so let's break it down, right? It was talking about how many grams of KCl, in this case, 8 grams of KCl, dissolved in enough water to form 50 grams of the solution. So we kind of have to read into the way it's phrased. So by breaking that down, we can see, well, there's my grams solute. I have 50 grams of the total solution, which is the solute mass plus the solvent. Oops, I don't know, I can't spell. Solute and solvent to get the mass of the solution, right? We do our math out, and we get our 16% m per m solution, or mass per mass. And like I said, we're going to see that equation look really similar pop up a couple more times. So volume per volume percent solution, really similar idea. The volume of my solute over the volume of my solution. We'll multiply that by 100%. That will be our percent volume per volume. We won't, oh no, I'm not even going to go there. Let's not confuse anyone with anything. Let's keep it simple. Let's stick with that. And just like what we saw with mass percent, right, we could also represent this as the number of mils of solution, or sorry, number of mils of solute that would be in a theoretical 100 mil solution. Again, it mostly comes from because we multiplied it by 100%. So it's nothing special. It's just the way we set it up. And so to basically unite those two ideas together, we had mass. So usually we say mass per volume per volume, and now we're on mass per volume. Again, we'll represent that just like we've been doing everything else, but now it's percent m over v. So because it's m over v, grams of solute over mils of solution times 100%. So all really similar ideas with similar equations. They are roughly, well, not they're trying to get across the same idea to the reader, but it's going to be up to you to be able to interpret between the three, plus also how to use those equations. And so the last way to represent concentration that we'll discuss in this chapter is going to be that of molarity. Like I said, this is the most common unit used in chemistry. So we'll be doing a lot of equations with molarity. So most common unit of concentration in chemistry, and in biology for that matter too. So just like with the other three units of concentration that we looked at, it's going to be amount of stuff per amount of solution. The only thing is the way we're going to keep track of stuff is now going to be in the units of moles. So again, we've noticed always on the numerator is the solute, denominator is solution. So I have moles of solute over, in this case, by the definition of molarity, is per liter of solution. And so if we had a 1 molar solution of NaCl, it is by definition 1 mole of NaCl per liter of solution. You'll notice we use this abbreviation a lot, and we may not have a 1 liter solution. It's mostly a way to represent the concentration as if you had 1 liter, you would have 1 mole of NaCl. We'll discuss in a couple other sections on what happens when we're dealing with something that's less than a liter, right? But it's mostly a mathematical relationship. Don't think too hard into it. 1 mole of NaCl dissolved in 1 liter would give me a 1 molar solution. So all this is a summary of the conversion factors. If you'd like, I didn't put it into the worksheet this time, but maybe copy and paste it and print it out for yourself. It's a good summary of all the different units that we're using for concentration. So it seems like a lot, but if you can nail them down, it's really not that bad. Because again, concentration is something you will deal with every day as a nurse, and it's not going to go away in chemistry. So let's move on to, once we have a solution, what if we need to dilute it? So the example that we have on the slide is just orange juice. I don't know if you guys have done this. I know back when I was a kid, so 10 or 15 years, whatever it was before you guys were born, you can buy orange juice in a can. It used to be a frozen concentrate, and then what you do, start with the concentrated orange juice, add water to it, and then you'd be able to mix it up, dilute it, create a solution, which you drink, which is orange juice, at the correct concentration. So this is actually really quite common. So most chemicals that you find in the lab, we call them stock concentrations because they happen to be easy to make because they're in very large quantities. And then you only have to make it once, and then you can just take small quantities out of that over several months instead of making a solution every day. And it's the same idea of delivering medication. You're not going to give 10 liters of medication to someone if you don't need it, right? You're going to add a small amount. And the way you usually do that is start with a high concentration and add a small volume. Will give you a small amount. So let's define what we mean by dilution, right? So for we'll define it for our class. Dilution is adding it to any solvent, but we're going to be talking about specifically, of when we dissolve into water. right? We've noticed that the volume of the solution is going to have to increase. It's the only way you can make a dilution. So that usually in real life doesn't pose a problem, but you have to take that into consideration, right? So as that volume increases, concentration will decrease, right? However, the mass of the solute is going to remain the same. Keep in mind, I did not say solution. The mass of the solution will most definitely increase because the volume of water increased. But the total amount of solute is not changing. It is unchanging, right? And so this is what we see down here. We have a pretty concentrated solution. This is a red dye 40, which absorbs light very strongly so that it appears red. And so if those molecules, if there's a lot per unit space, so if I have a lot of moles per unit space, maybe this space is measured in liters, we can see that that's what molarity is. If I add more of my solvent, in this case I don't know what it is, usually a red cap means acetone, but doesn't matter, it's going to be our solvent. When that volume is increased, the same number of particles are there, so the mass doesn't change. But what you effectively did is you decreased the solution, because it's still N over liters, so moles over volume, but you increased the volume. So there's going to be less stuff per unit area, and that's actually why it appears more dilute than over here. You can see it's orangey versus dark red. So I've included what the book gives you as equations, but they're exactly the same equation. You do not need, I don't know why they give you two. One for percent concentration and one for molarity. Pick one and stick with it. I have seen books that use C1 V1 equals C2 V2. For whatever reason, this tends to be the most common and usually taught in high school. I mean, I've used this probably a million times in my life. M1 V1 equals M2 V2. Most students love this equation, but it is only used for dilutions. It is used for nothing else when making a solution. Only used for dilutions. Everyone just likes to fall back on this equation of how simple it is. So to break down what it is, it's just saying if I know the concentration or the molarity, it's the only difference between C and M, it's just a name. If I know the concentration or molarity, and at the initial volume, I can make a dilution to a new volume and then immediately figure out what the concentration is of that second solution. So we'll use this a couple of times because it's an important equation, and I'll do a lot more of problems like this on the study check video. So let's start with this. We'll read through. So it says, what is the final concentration? So that's where we're asking to find C2 or M2, whatever you want, right? When a 50-liter solution of 6 molar HCl, so that is my initial, 0.5 liters. So that's my initial volume of my concentrated solution, right? So what is the final concentration when this solution is diluted to a final volume of a liter? So my final volume is 1 liter. If I sketch what that looks like, we'll make this the 1 liter mark. There's a half a liter. It means I started at this volume with one amount, so one concentration or one molarity. Doesn't really matter if I use C or M. And then I dilute it. Sorry, I did a poor job of that. Wow. If I have the same container, but now I have diluted it to 1 liter, the concentration is definitely going to go down because now I have the same amount of stuff in a larger volume. So we take a stock. We can either use C1 V1 equals C2 V2 or M1 V1 equals M2 V2. They're not exclusive. So here we've gone with this form. And we make sure we have all the information we know. We got C1, yup. We got V1, yup. I got V2, yup. I have something to solve for, I most certainly do. So I'm in good shape. And that's exactly what we have here. So what can we do? Well, what I like to do, and you've seen in some of my other videos, is instead of before adding numbers and units, because it can make things messy very, very quickly, is to rearrange the equation to solve what I want for. So I'm trying to find, I don't know why it switched from C's to M, sorry about that. Again, I can put this back up here to make sure we don't get confused. I'm saying they're the exact same, equation. So if I start there and I'm searching for M2, this is the variable I want. If I divide both sides by V2, it's exactly what I get. M1 times V1 over V2. Those are the three variables that I know. I could go back one slide, but it's kind of disruptive, so hopefully you wrote that down. There's my M1 of 6 molar. It used to be in 0.5 liters, and it's been diluted to a new concentration of 1 liter. The volume doubled, concentration halved. There's a 1-to-1 relationship, usually, right? So in that case, we double check, you double the volume, you halve the concentration. I started at 6, it's now at 3. And it's about as hard as it gets for dilution problems right now. So, properties of solution. Like I said, too, there's actually quite a bit of... I should probably take 2 seconds to pause on that, right? This was only one representative example to do during this lecture. This is about as hard as it gets, but there's a lot of different ways we could play with the equation, and I give you a couple of those on the study check video. So this will be our last section for Chapter 9, and it's talking about properties of solution. So, how do I know if something's a solution versus not a solution? Everything we've talked about so far, I've just said it is a solution, right? But ways we can take observations, or know how a solution was made, or maybe do experiments to figure out if something's a solution or not, and that's what we'll talk about in this chapter. So first off, solutions are transparent. This doesn't mean they don't have color, it just means you can dilute them enough that you can see light through it. So all solutions would be transparent. If you let the solution sit, it's not going to separate. And what do I mean by that? You take a like salad dressing and shake it up. It kind of looks like it's homogeneous, but if I let it sit, it will separate into a water and an oil level layer. Same idea if you have sand inside like a bucket, right? If you swirl it around, you can get it to be a slurry, but if you let it sit, the sand will separate out. And sand and water is not a solution, right? So solutions, by definition, contain small particles, ions, or molecules that cannot be filtered or pass through a semi-permeable membrane. For us, this kind of increases the complexity of what we're talking about. These are the two definitions we're going to use for determining if something's a solution versus two new terms we're going to cover, which are colloids and then suspensions. And it will be these two, filtering and semi-permeable membranes, which we'll define in a little bit, that is going to allow us to determine, is it 1, 2, or 3? So what is a colloid then, if we already defined what a solution is? Well, a colloid are going to have, instead of having small or tiny particles, they're medium-sized particles. However, even though, remember, this is medium compared to the size of an ion, which is incredibly small, right? So medium-sized particles might be, you can have colloidal suspensions of some moderately soluble ions. So you might see like milk of magnesia, things like that, where you need to be kind of, they need to be shaken. If you let them settle, they could split, but you can't necessarily filter it out. So they cannot be filtered. However, they can be separated out by a semi-permeable membrane. So a more common thing you might see for that, and we'll talk a little bit more about that, will be dialysis, right? So you can have a colloid suspension of protein. So it's going to behave as one solution, but proteins are rather massive particles compared to small ions. You can't separate proteins out through filtration, but you can definitely separate them out by a semi-permeable membrane. And if you're wondering, we'll get to it in a second. Maybe I can just define that here, what semi-permeable means. So what it means is it only allows, so it's semi, so it means it's not, the rule doesn't apply all the time. It's only semi-permeable. Only sometimes things can get through it. What effectively means is it's something made out of tiny pores. Commonly, which if you do biochemistry, they're dialysis bags. The pores are teeny tiny so that water can go through. But if you have something more massive, like DNA or protein or something like that, they're too big to go through the holes and they'll stay on one side. So it's a semi-permeable membrane because only some stuff can go through. So what it basically means is colloids are big enough that it's difficult, very difficult, to design a sieve that has fine enough mesh pores to separate things out. So other examples of colloids, right? So fog or hairspray, dust, smoke. Mayonnaise is actually a colloidal suspension. Eggs act as a homogenizer for water, the water in the eggs, and then also the oil that you use to make mayonnaise. Homogenized milk, again, you've probably heard that word, that's to make sure none of the proteins separate out. And so you can read through these yourself, but colloids are actually fairly common, despite maybe not being a common word. So we've covered the first two of solutions versus colloids, and now we're on to suspensions. So these, by definition, are no longer homogeneous. The other two were. It is now heterogeneous, and it's going to be a non-uniform mixture. They're typically very large particles that, when allowed to sit, will settle out of solution. So that might be something like sand and water, or maybe something like, I don't know, like I've said before, whatever, that's a good enough example. Whatever I said before, too. Oh, salad dressing, right? Again, we can filter out a suspension because it's going to be caught up by even something as simple as a coffee cup filter. And it can be stirred must be stirred to stay suspended. So it's the same idea with sand and water. All right. Oop, there we go. And so I know I did a lot of talking, so if you don't need all of that explanation, here is a really good summary of everything we just talked about. I really like this this figure does a good job of demonstrating visually the difference between a solution, a colloid, and a suspension. So at point A, you're just allowing some time to pass. So anything that is part of a suspension is going to then settle to the bottom. So then we can go to the next step. Can I filter some things out, right? So maybe if I didn't get all of the suspension out, maybe I was impatient, so there was some hanging around. I pass it through, well, it's getting stuck in the filter. So again, suspension can be filtered. Oops. Let me do it in order, actually. So it can settle and be filtered. So we're left over here. Take a look after we've filtered and let settle. Now we only have colloids and a solution. How do we separate out a colloid? Well, we said we could use a semi-permeable membrane because that's going to let really small things through, like water, and keep really big things through out, kind of if they're more like macroscopic. So we call them macromolecules, which is like DNA, protein, etc. And then water could flow through. Right? It doesn't have to be. I just know biological examples. That's all. And so what we see here, even if we still didn't get the suspension out, it'll be stuck inside the bag. And then we also see the colloid. Oops. Must be showing in the middle of a process. We're showing that the colloid is getting definitely stuck in the bag as we're watching solute particles, the small ones, move out. So I really like that visual. The last thing we're going to talk about is osmosis. So this is going to be important for dialysis in nursing. So we need to, this is probably one of the more things we should focus on, just in terms of definition, right? So it seems intuitive because it is, but sometimes figuring out direction of water flow is not. So where's the water going to flow? So water for us is always going to be our solvent. It's going to flow from a lower to higher solute concentration. And so that's what we see over here in this figure. So we have a solution of water and it's separated by a semi-permeable membrane. One side has more solute, is in a greater concentration. So what's going to happen is the water flows from low to high concentration. Why? Because what it's trying to do is dilute out that high concentration of solute. So it always flows from low to high because it's trying to even the playing field. Excuse me, I'm going to cough for a second. Don't worry, that's just dry throat from talking a lot. So let me have a sip of water. All right. So The level of the solution, which has the higher solute, the concentration rises. That is, wait, did I write that right? The level of the solution with the higher solute concentration rises. You know what? Ignore that. That is phrased incorrectly. What I'm trying to say is that the level of the water itself is going to rise as it's trying to dilute out the water here. So actually water level will drop here and increase on the other side of the semi-permeable membrane, trying to reach the same concentration. So white might not make it there, but it usually will go theoretically until they're both the same concentration. So to summarize, water flows into the solution with a higher solute concentration until the flow of water becomes equal in both directions. So that just means there's equal concentration on both sides of the semi-permeable membrane. That brings us this idea of osmotic pressure. So, oops, I keep using the wrong tool. So what is it, right? So if we're thinking of what's happening, if we, again, had some, this might defy the laws of physics right now, but it will help demonstrate what I'm trying to get across. So this highlighted line, ooh, where did it go? Come back. This highlighted line is going to be our semi-permeable membrane, so SPM. Let's say we got a pretty high concentration, so I'll make it 2, 3, 4, 5, 6 dots over here, and a low concentration over here. And I'll use a blue marker to represent water. So, oops, blue will be water. And then red is our solute. Whatever that may be. So initially, they'll start at the same level of, because we filled them up, right? What ends up happening, though, is water on this side, this left-hand side, this is low concentration. This is high. To try and get them at the same concentration, water is going to pump across the semi-permeable membrane, raising the layer of water here. So if I kind of erase some of these lines, what we'll end up seeing is the water level will drop on one side. And let's get back to blue. And the water level will increase on the other side, because what it's trying to do, again, is decrease the concentration on the high side and increase the concentration on the low side. So eventually what they'll do is they'll get to the same concentration. So 2, 4, 5, 6, I had 6 of them there, right? Eventually they'll reach the same concentration. What is osmotic pressure? It's the amount of force you actually have to press back on that raised column of water and then to force it against the gradient to refill back up what you lowered. So basically how much force it takes to get back to the original starting level where both the solutions were at the same height. So that's what osmotic pressure is. A little bit confusing, right? But we're going to give a couple of examples. So instead of osmosis being the forward process, right, where we saw water goes from low to a high concentration, and what it will do is effectively, it dilutes this out, but it's not necessarily purifying the water. The water is freely going back and forth. If you reverse the process of osmosis, what you can do is have a semi-permeable membrane with a high concentration on one side and then no solute on this side, and you can force water from high to low through reverse osmosis by putting pressure on the top and forcing the water through a semi-permeable membrane, effectively purifying it. And so because it's the reverse process, it's called reversed osmosis. And so the reason why it's covered is because you've probably heard the phrase before, but probably didn't know what it meant. But it literally just means doing osmosis in reverse. It requires work, though, to push the water backwards against the gradient. So when dealing with osmotic pressure, there's going to be 3 different types of solutions we're going to look at. One is going to have the same concentration of solutes on the other sides of a semi-permeable membrane. We'll use red blood cells as our example. Then we'll talk about hypotonic and hypertonic. So what happens when the solution has a concentration lower than what's inside blood cells versus higher, right? We're talking nutrients and I can't think of words. Nutrients and ions and salts, right? So an isotonic solution, as definition, it means the concentration outside the cell is the exact same concentration on the inside of the cell, so there's no osmotic pressure. Water can just freely dissociate between the two, and then what you're going to get is basically the cells retain their normal volume. So if we break down the word, iso equals same in Greek. Tonic is talking about dissolved solutes to make a solution. That's why we call it tonic water, because it's dissolved CO2 in water to make a solution of tonic water. So what we need to care about really is the prefix. So iso is going to mean same in Greek. The second type of solution we'll talk about is hypotonic. So hypotonic means the solution outside the red blood cell, right, is actually going to be lower than inside. And that will be the concentration of whatever's inside the blood cells, right? So because the concentration is lower, right, that means water is going, it's lower. So that means water is going to go and try to dilute the molecules that are inside the red blood cell. So what they're actually going to do, water is going to force itself inside the red blood cell to try and dilute the inside. What this will cause is hemolysis. And hemolysis, we break that down, heme being, which usually refers to blood, though technically has a different definition if you do biochemistry, but we'll deal with blood, so it'd be blood cells. And then lysis means to cut or burst. So what it's actually doing is going to cause the blood cells to burst, so it breaks them open, because under the sheer, just the force of water coming in, causes them to swell and then explode. The last type of solution we'll talk about is hypertonic. Oh, I showed those on the last slide, but if we're breaking down the Greek again, hypo is going to be low or before. That's why you call it hypothesis. We're going to go with the low definition. And then we also have hyper. Hyper being high or higher, right? So we'll care about low and high. So a hypertonic means the concentration of solutes is higher than inside the red blood cells. What this will cause is a different scenario. Now the solution outside the blood cells is higher concentration than inside, so water will actually rush outside of the cells. I drew that weird, but it will rush out of the cells to try and dilute that high concentration of salt that is surrounding it, or biomolecules, and this is going to be called crenation. So when we look at a crenated cell, right, it's in a hypertonic solution. It means water will leave the red blood cells and will cause them to shrink. And I believe where this red etymology comes from, though I'm not 100% sure, is crenations being, I think in geology, doesn't that mean like spiky outcroppings? I may be totally wrong, but that's what basically it looks like to me. So hopefully I'm right. I can double check that though for you guys. All right, so this will be the last thing we talk about. Now we've discussed semi-permeable membranes, osmosis, osmotic pressure, defined isotonic, hypotonic, and hypertonic. Now we'll just talk really quickly about dialysis. Mostly not the theory of how it actually works in the hospitals, but, not how it actually functions as like in the hospitals, but the theory that is used behind the instruments in hospitals. So dialysis, right? So solvent and small solute particles can pass through an artificial membrane. So if we had some sort of artificial membrane, in biochemistry, we usually use cellulose. I don't know what the semi-permeable membrane is in like instruments used inside hospitals. But effectively what it does is let small particles out or through. Small go through and the large are left behind, right? Just like we talked about any other semi-permeable membrane. So large particles are retained inside, allowing other things to pass through. So waste particles such as urea from the blood can be removed using hemodialysis. Again, that's talking blood dialysis. Again, right? Blood removing. So actually dialysis, I'm not 100% sure how to break that etymology down. But that's what basically an artificial kidney does. So what it's going to do is it keeps behind good large molecules like cells and plasma, DNA, and I don't know what else is in blood. I'm not a MD at all, right? But smaller molecules can pass through, like if it depends on how it's set up, but maybe small molecules like urea would pass through and you just throw it out, right? So that's how you might use the theory of dialysis in a nursing setting. All right, that was a little bit long at 35 minutes. I'll keep working on trying to make these as condensed as I can without losing any additional information. All right, so that ends our lecture component for Chapter 9.